Tonight we're going to talk about a particle that is breaking physics, not in some dramatic, explosive way, in a quiet, almost invisible way. Scientists measured something about a tiny subatomic particle called the muon, and the number they got back was wrong. Not wrong by a lot, music wrong by a whisper, but in physics, a whisper can be a scream, because the standard model of particle physics is the most successful scientific theory ever constructed. It has predicted the behavior of the universe with staggering, almost absurd accuracy for over 50 years. And now one measurement confirmed again and again across decades of experiments refuses to match what the theory says it should be. Something is missing from our understanding of reality, and nobody knows what it is. Before we dive into this, if you find these kinds of deep explorations of science fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, settle in and make yourself comfortable. Let's begin. Let's start with something that might seem like a strange question. Music, what is the universe actually made of? Not philosophically, physically. What are the fundamental ingredients of reality? If you took everything apart, music, every mountain, every ocean, every star, every person, and broke it all down into the smallest possible pieces, what would you find? Humans have been asking this question for thousands of years. The ancient Greeks had an answer. They believed the universe was made of 4 elements: earth, water, air, and music, fire. Everything around you was supposedly some combination of these 4 substances. A rock was mostly earth. A river was mostly water. The wind was air, and the sun was fire. It was elegant and intuitive, and it was completely wrong. But it was an honest attempt to do something extraordinary to reduce the overwhelming complexity of the world into a small number of simple ingredients. That impulse, the belief that beneath the chaos of everyday experience, there are simple rules and simple building blocks, has driven physics for its entire history. And it turned out to be right, just not in the way the Greeks imagined. For over 2 zeros, 0 years, that was roughly where things stood. Different cultures had their own versions of elemental theories. Chinese philosophy described 5 elements. Indian traditions described 5 as well, though different ones. But the core idea was always the same. The universe is complicated on the surface, but simple underneath. Find the simple parts, and you understand everything. Alchemists in the Middle Ages tried to transform one substance into another, working from the assumption that all matter shared common building blocks, music, that could somehow be rearranged. They never succeeded in turning lead into gold, but their experiments laid groundwork for something far more valuable: real chemistry. In the late 1700s and early 1800s, scientists began to realize that the Greek model was far too simple. The universe wasn't made of 4 elements. It was made of many elements: hydrogen, oxygen, carbon, nitrogen, iron, gold, dozens of distinct substances that couldn't be broken down further by chemical means. By 1869, the Russian chemist Dmitry Mendeleev had organized these elements into the periodic table, arranging them by their properties and atomic weights. The table revealed patterns. Elements in the same column behaved similarly. There were gaps in the table that predicted the existence of elements not yet discovered. And when those elements were eventually found, they had exactly the properties Mendeleev had predicted. It was a stunning triumph. The periodic table was one of the great achievements of 19th century science, a moment when the apparent chaos of the material world revealed hidden order. But this raised a deeper question. Why were there so many elements, And why did they have the properties they did? Why was gold heavy and soft, while iron was lighter and hard? Music, why did some elements react violently with water, while others were completely inert? Why did the table have the structure it had? The periodic table organized the elements beautifully, but it didn't explain them. It was a map, not a theory. It told you what was there but not why. The answer came in stages throughout the late 19th and early 20th centuries. In 1897, the British physicist J.J. Thomson discovered the electron, a tiny negatively charged particle that was a component of all atoms. This was revolutionary. It meant atoms weren't truly indivisible. They had internal structure. They were made of smaller things. In 1911, Ernest Rutherford fired alpha particles at a thin sheet of gold foil and discovered that most of the atom's mass was concentrated in a tiny, dense, positively charged nucleus. The atom was mostly empty space with a small, heavy center and light electrons orbiting around it. By the 1930s, physicists had identified two particles inside the nucleus: protons, which carry positive electric charge, and neutrons, which carry no charge at all. The number of protons in an atom's nucleus determined what element it was. Hydrogen had 1 proton, helium had 2, carbon had 6, iron had 26, gold had 79. The periodic table suddenly made sense at a deeper level. The properties of elements were determined by the structure of their atoms, which was determined by how many protons, neutrons, and electrons they contained. This was extraordinary. The entire complexity of chemistry, the richness of materials and substances and reactions that make up the physical world, could be understood in terms of just 3 particles: protons, neutrons, and electrons. 3 building blocks explained everything from water to steel music to human DNA. But physicists weren't satisfied because they had also discovered something else, something that complicated this beautifully simple picture. They discovered new forces and new particles that didn't fit neatly into the atomic model. By the middle of the 20th century, physics was in a state of productive chaos. Particle accelerators, machines that smash particles together at enormous speeds, were revealing a zoo of new subatomic particles. Pans, cons, lambda particles, sigma particles, z particles, omega particles, dozens of exotic particles with strange names and stranger properties. They appeared in cosmic ray experiments and in collisions at accelerators, lived for tiny fractions of a second, and then decayed into other particles. It was bewildering. Instead of the universe getting simpler as physicists dug deeper, it seemed to be getting more complicated. The physicist Willis Lamb, upon accepting his Nobel Prize in 1955, reportedly joked that he had once thought the discoverer of a new elementary particle used to be rewarded with a Nobel Prize. But now such a discovery ought to be punished by a $10,000 fine. Where were all these particles coming from? Why were there so many? What rules govern their behavior? It took decades of theoretical and experimental work, carried out by hundreds of physicists across multiple countries, to sort through this mess and arrive at something coherent. And what they eventually built was arguably the greatest intellectual achievement in human history. They called it the Standard Model of Particle Physics. The Standard Model is a theoretical framework that describes the fundamental particles that make up the universe and the forces through which those particles interact. It is not a single equation or a single insight. It's a comprehensive mathematical structure developed over several decades that unifies our understanding of 3 of the 4 known fundamental forces of nature: Music, the electromagnetic force which governs how charged particles interact with each other and is responsible for light, electricity, music magnetism, and the chemical bonds that hold molecules together. Every time you see a color, feel the warmth of sunlight, or touch a solid object, you're experiencing the electromagnetic force, the strong nuclear force which holds protons and neutrons together inside atomic nuclei and prevents positively charged protons from flying apart due to their electromagnetic repulsion. Without the strong force, no atomic nucleus heavier than hydrogen could exist, and the universe would contain nothing but isolated protons and electrons drifting through space. Music, no stars, no planets, no chemistry, no life, and the weak nuclear force which governs certain types of radioactive decay and plays a crucial role in the nuclear reactions that power the sun. The weak music force is responsible for the process that converts protons into neutrons inside the sun's core, releasing the energy that sustains all life on Earth. The only force the Standard Model does not include is gravity. Not because gravity isn't important, but because physicists have not yet figured out how to incorporate gravity into the same mathematical framework as the other three forces. Music, general relativity. Einstein's theory of gravity, music works beautifully on large scales. The Standard Model works beautifully on small scales, but combining them into a single unified theory remains one of the great unsolved problems in physics. So, what does the Standard Model actually contain? At its core, the Standard Model says the universe is made of 12 fundamental particles of matter divided into two families, 6 quarks and 6 leptons. Music, the quarks come in 6 varieties or flavors: up, down, charm, strange, top, and bottom. Quarks are never found alone in nature. They always combine in groups bound together by the strong force. A proton is made of 2 up quarks and 1 down quark. Music, a neutron is made of 1 up quark and 2 down quarks. All the exotic particles discovered in the mid-10th century, the pines, cows, and the rest, turned out to be different combinations of quarks. The zoo suddenly made sense. It wasn't that there were hundreds of fundamental particles. There were just a handful of quarks that could combine in different ways to create the diversity physicists had observed. The leptons are the other family. There are 6 of them as well. The electron, which you already know, the electron neutrino, a nearly massless particle that barely interacts with anything. Music, and then 4 more. The muon and its associated muon neutrino, and the towel and its associated towel neutrino. These 6 leptons are organized into 3 generations. The first generation contains the electron and the electron neutrino. These are the lightest and most stable. They're the particles that make up ordinary matter, the stuff you interact with every day. The second generation contains the muon and the muon neutrino. The third generation contains the tau and the tau neutrino. Each generation is heavier than the last. The muon is about 207 times heavier than the electron. The tau music is about 490 times heavier than the electron. But aside from their mass, these particles are identical to their lighter counterparts. The muon behaves exactly like an electron in every way except that it's heavier. Music, this is one of the great mysteries of particle physics. Why are there 3 generations? Why does nature repeat itself with heavier copies? Nobody knows. In addition to these 12 matter particles, the Standard Model contains force-carrying particles called bosons. The photon carries the electromagnetic force. When 2 charged particles repel or attract each other, they're exchanging photons. The gluon carries the strong force. There are 8 types of gluons, and they bind quarks together inside protons and neutrons. The W and Z bosons carry the weak force. Music, they're responsible for certain types of radioactive decay and play a crucial role in nuclear fusion inside stars. And then there's the Higgs boson, discovered in 2012 at the Large Hadron Collider at CERN. The Higgs boson is the particle associated with the Higgs field. Music, a field that permeates all of space and gives particles their mass. Without the Higgs field, particles like electrons and quarks would be massless and would travel at the speed of light. The universe as we know it with atoms and molecules and solid matter would not exist. That's the standard model. 12 matter particles, 4 force-carrying bosons and the Higgs boson, 17 fundamental particles in total. And from these 17 particles and the rules governing their interactions, music, you can derive essentially all of chemistry, all of nuclear physics, all of atomic physics, and all of the behavior of light and electricity and magnetism. Music, it's an astonishingly compact description of reality. But what makes the standard model truly extraordinary isn't just that it works. It is how well it works. The standard model doesn't just give rough approximations. It gives predictions of almost absurd precision. Predictions that have been confirmed by experiment again and again and again. The magnetic moment of the electron, for example, has been calculated using the standard model to more than 10 decimal places. And when experimentalists measured it, the measurement agreed with their prediction to more than 10 decimal places. Music, that's like predicting the distance from New York to Los Angeles to within the width of a human hair. No other theory in any field of science has ever achieved that level of agreement between prediction and measurement. Nothing even comes close. The standard model predicted the existence of the W and Z bosons before they were discovered. It predicted their masses. When the bosons were found at CERN in 1983, their masses matched the predictions. The standard model predicted the existence of the top quark, the heaviest quark, and estimated its mass. When the top quark was discovered at Fermilab in 1995, the mass matched. The standard model predicted the existence of the Higgs boson and constrained its mass to a range. When the Higgs was found in 2012, it fell squarely within the predicted range. For over music 50 years, the standard model has passed every test thrown at it. Experimentalists have tried to break it to find some measurement that disagrees with its predictions to discover some particle or some behavior that the model can't explain. And for decades, it has stubbornly refused to break. It just keeps being right. But physicists know the standard model is not the final answer. It can't be because there are things it doesn't explain. Glaring obvious things that tell us the standard model, for all its success, is incomplete. It doesn't include gravity, the force that holds you to the Earth, that keeps planets in their orbits, that shapes the large-scale structure of the universe, is simply missing from the standard model. It doesn't explain dark matter, the mysterious invisible substance that makes up about 27% of the universe's mass-energy content. We know dark matter exists because galaxies rotate too fast to be held together by the gravity of their visible matter alone. Something else is there, something massive and invisible, and the standard model has no particle that could account for it. It doesn't explain dark energy, the even more mysterious force that's causing the universe's expansion to accelerate. Dark energy makes up about 68% of the universe's total energy content, and we have essentially no idea what it is. It doesn't explain why there's more matter than antimatter in the universe. Music, the Big Bang, should have produced equal amounts of matter and antimatter which should have annihilated each other completely, leaving behind nothing but radiation. Yet here we are. Something tipped the balance in favor of matter, and the Standard Model can't fully explain what it doesn't explain. Neutrino masses, at least not in its original formulation. Neutrinos were originally assumed to be massless in the Standard Model, but experiments in the late 1990s showed that they do have mass, albeit incredibly tiny masses. And it has too many free parameters, numbers that have to be measured experimentally music and plugged in by hand rather than being predicted by the theory itself. There are about 19 of these free parameters, including the masses of the quarks and leptons music and the strengths of the forces. The Standard Model doesn't tell you why the electron has the mass it does, or why the strong force has the strength it does. These values just are what they are, and you have to measure them. So, physicists have long suspected that the Standard Model is not the complete story. Music, it's an incredibly good approximation, but there must be something deeper, something more fundamental that explains the things the Standard Model can't. The question is, how to find it. How do you discover what lies beyond the most successful theory in scientific history? One approach is to build bigger particle accelerators and smash particles together at higher and higher energies, hoping to produce new particles that music, the Standard Model, doesn't predict. This is what the Large Hadron Collider at CERN does. Music, and it did discover the Higgs boson, which was a triumph. But since then, despite enormous effort and billions of dollars of investment, the LHC has not found any particles beyond those predicted by the Standard Model. No supersymmetric particles, no extra dimensions, no evidence of compositus, nothing that clearly points to new physics. The other approach is precision. Music, instead of going bigger and higher energy, you go smaller and more precise. You take a quantity that the Standard Model predicts with extraordinary accuracy, and you measure it with even more extraordinary accuracy. If the measurement disagrees with the prediction, even by a tiny amount, that tiny discrepancy could be a window into whatever physics lies beyond the Standard Model, a crack in the edifice through which you can glimpse something new. This approach is sometimes called the intensity frontier, as opposed to the energy frontier represented by machines like the LHC. Instead of trying to produce new particles directly by slamming things together at enormous energies, you look for the subtle fingerprints that new particles leave on familiar processes. Virtual particles don't need to be produced directly. They exist as quantum fluctuations. Music and their effects, however tiny, can be detected if you measure precisely enough. This is where the muon enters the story. The muon was discovered in 1936 by Carl Anderson and Seth Needham while studying cosmic rays. Cosmic rays are high-energy particles, mostly protons that rain down on Earth from space. They come from all directions, produced by violent astrophysical events like supernova explosions and active galactic nuclei. When these energetic particles hit the upper atmosphere, they collide with nitrogen and oxygen atoms and produce showers of secondary particles that cascade downward toward the surface. Anderson and Needham found a particle in these showers that was heavier than an electron, but lighter than a proton. It had the same electric charge as the electron, -1, and it behaved like an electron in almost every way, but it was about 207 times heavier. Initially, some physicists thought this new particle might be the particle predicted by the Japanese theorist Heike Yukawa, who had proposed a medium-mass particle as the carrier of the strong nuclear force. Music, but experiments soon showed that the muon didn't interact strongly with atomic nuclei the way particles should. It passed through matter almost as easily as a neutrino. The Moon wasn't the strong force carrier. It was something else entirely, something unexpected. Nobody expected this particle. It didn't seem to serve any obvious purpose. It wasn't a building block of atoms. It wasn't needed to hold nuclei together. It just showed up in cosmic ray experiments, lived for about two microsecons, and then decayed into an electron and two neutrinos. The physicist Isidore Isaac Rab, I famously quipped, who ordered that, when he learned about the Moon. It was a funny line, but it captured a genuine puzzle. Why did this particle exist? What role did it play? Decades later, we still don't have a fully satisfying answer. The muon appears to be simply a heavier copy of the electron. Music, it participates in the same forces. It has the same electric charge. It has the same spin. Music, the only difference is its mass. In the Standard Model, the muon is a second-generation lepton. It sits in the second row of the particle table, heavier than the electron, but otherwise identical. It's as if nature built the electron, liked the design, and made a heavier version for reasons it hasn't shared with us. But that extra mass turns out to be incredibly important for one particular measurement, the measurement of the muon's anomalous magnetic moment. And this is the measurement that is now threatening to crack the Standard Model wide open. Every charged particle that spins acts like a tiny magnet. It has what physicists call a magnetic moment. The strength of this magnetic moment depends on the particle's charge, its mass, and its spin. For a simple charged particle with spin 1/2 like the electron or the muon, a straightforward calculation from basic quantum mechanics predicts that the magnetic moment should have a specific value. Physicists express this in terms of a number called g. The basic prediction is that g equals exactly 2. But the real world is more complicated than the basic prediction. In quantum field theory, the framework that underlies the Standard Model, empty space, is not really empty. It's seething with activity. Pairs of virtual particles constantly pop into existence music and annihilate each other. These virtual particles are not directly observable. They exist for incredibly brief moments. Borrowed from the uncertainty principle of quantum mechanics music, and they vanish almost as soon as they appear. But during their fleeting existence, they interact with real particles. They affect the properties of real particles in subtle music, but measurable ways. When a muon sits in a magnetic field, its magnetic moment is affected by all these virtual particles buzzing around it. Virtual photons, virtual electrons, virtual quarks, virtual W and Z bosons, even virtual Higgs bosons. Every particle in the Standard Model contributes something to the muon's magnetic moment. Each contribution shifts the value of g away from exactly 2 by a tiny amount. The total shift is called the anomalous magnetic moment, and physicists denote it as A. It's defined as g minus 2 all divided by 2. This number A is tiny. For the muon, it's approximately 0.0016592. That doesn't look like much. It's barely more than 1/10th of 1% above zero. But this tiny number encodes an enormous amount of physics. Every force, every particle, every interaction in the Standard Model contributes to it. Measuring this number precisely and comparing it to the theoretical prediction is like taking the temperature of the entire Standard Model at once. Here's the key insight. If every particle and force in the Standard Model contributes to the muon's anomalous magnetic moment, then this number is sensitive to everything the Standard Model contains. But it's also potentially sensitive to particles and forces the Standard Model does not contain. If there are new particles out there, particles we haven't discovered yet, particles not included in the standard model, they would also create virtual pairs. They would also pop in and out of existence around the muon, and they would also contribute to the muon's magnetic moment. The contribution would be small because if these new particles were obvious, we would have found them already, but it would be there hiding in the last few decimal places of the measurement. This is why physicists became so interested in measuring the moon's G-2 with extreme precision. Because a discrepancy between the measured value and the standard model prediction, even a tiny one, could be evidence for new physics, for particles or forces that we haven't discovered yet for whatever lies beyond the standard model. And there's another reason the muon is special for this measurement, and it has to do with music, its mass. In quantum field theory, the contribution of heavy virtual particles to the magnetic moment scales with the square of the particle's mass. The heavier the particle you're measuring, the more sensitive its magnetic moment is to whatever new heavy particles might be lurking out there in the quantum vacuum. The electron's magnetic moment has been measured more precisely. Music, but the electron is so light that it's almost blind to the heavy particles that could constitute new physics. The muon, being so much heavier, is vastly more sensitive. It feels the tug of heavy virtual particles that the electron simply cannot detect. And unlike the tau lepton, which is heavier still and would be even more sensitive, the muon lives long enough to actually be studied. Its lifetime of a little over 2 microseconds might sound absurdly brief, but in the world of particle physics, it's generous. Music, it's long enough to create beams of moons, store them in magnetic fields, music, and make extraordinarily precise measurements of how they behave. The muon occupies a unique position in the particle zoo. Music, it's the Goldilocks particle for this measurement. Not too light, not too short-lived, music, but just right. So, the stage was set. The standard model, the most successful theory in the history of science, makes a precise prediction for the moon's anomalous magnetic moment. If that prediction matches the measurement, the standard model survives another test. But if the prediction and the measurement disagree, if there's a discrepancy that can't be explained by experimental error or theoretical uncertainty, then something is wrong with our picture of reality. Something is missing. Something new is hiding in the gap between theory and experiment. And over the past several decades, that's exactly what appears to have happened. Experimentalists measured the moon's magnetic moment. Theorists calculated what it should be, music, and the two numbers didn't quite match. The difference was small, incredibly small. A difference that shows up only in the 9th or 10th decimal place, but it was persistent. It showed up in one experiment, and then another, and then another. Each measurement confirmed the same thing. The muon's magnetic moment was slightly larger than the standard model predicted. Something was making the moon slightly more magnetic than it should be. Something beyond the known particles and forces was tugging at the muon, nudging its magnetic moment just a fraction higher than theory allows. This discrepancy, this tiny gap between prediction and measurement, has become one of the most closely watched numbers in all of physics. It has consumed the careers of hundreds of scientists across multiple decades and multiple continents. Because if it holds up, if it survives every check and every scrutiny, it could be the first confirmed failure of the standard model, the first concrete evidence that there are particles and forces in the universe that our best theory doesn't know about, the first crack in the edifice through which we might glimpse the next revolution in physics. But to understand what that crack really means, we first need to understand how experimentalists manage to measure something so incredibly tiny. Music, because measuring the Moon's magnetic moment too, the precision required is one of the most extraordinary experimental achievements in the history of science. And that story begins with a ring, a giant superconducting 50-foot wide ring of magnets that had to be transported halfway across the United States, music, on a flatbed truck in the middle of night. So, how do you actually measure the magnetic moment of a moon? Think about what we're dealing with here. A particle that exists for barely 2/millionth of a second before it vanishes forever. Music in the time it takes you to blink, roughly 300 milliseconds, about 150,000 moons. Music could be born and die. And you need to measure a property of this particle, music, its magnetic moment, to a precision of better than 1 part per billion. Not 1 part per 100, music not 1 part per million, 1 part per billion. That's like measuring the distance from New York to Los Angeles and getting it right to within a fraction of an inch, except you're doing it on a particle that barely exists before it disintegrates into other particles. This is one of the most difficult and demanding measurements in all of experimental physics. And the story of how scientists pulled it off spans decades, multiple countries, and some of the most creative engineering the world has ever seen. The first measurements of the muon's anomalous magnetic moment began at CERN, the European Organization for Nuclear Research in Geneva, Switzerland, in the late 1950s, music, and early 1960s. These early experiments were groundbreaking for their time, but they were relatively crude by modern standards. The basic idea was simple in principle. You put moons in a magnetic field, watch how their spin behaves, and extract information about their magnetic moment from the results.